welcome to Normalized Logs and Beyond with our speakers Brian Maloney and David Levitsky.
Hey everyone, good afternoon. Thanks for sticking with us for one of the last talks of the day. My name is Brian Maloney and this is David Levitsky, and we work together to build a cloud-native threat detection pipeline and platform for Benchling. Now, what is Benchling, you might ask? Benchling is a software as a service platform that powers some of the world's most cutting-edge biotechnology research, with customers ranging from 2 scientists and a molecule startups to some of the largest biotech companies around. Needless to say, Benchling protects some extremely sensitive data on behalf of their customers and needed a scalable and reliable solution for detecting threats to that data while retaining maximum flexibility for an unknown future. Our work resulted in a platform built on replaceable components using a combination of AWS technologies and off-the-shelf software, which is the subject of this talk. And just one last note about Benchling. We are hiring, so if you're interested, maybe come talk to me. But first, let's just briefly go over the steps of threat detection. For those of you who might be primarily offensive practitioners, or if you're just new to the field, you can think of this kind of as just a brief Blue Team 101. So this is kind of the overview of the steps, from collection to normalization and enrichment, detections running on that, security alerts, going into investigations, and then response actions. So what about collection, right? We start on the left with collection. We need the data to do our work. Collection, I think of it as like the hard part. Any modern organization of any significant size is going to have a ridiculous number of security data sources, from your enterprise identity and your HR applications, things that you use to run your business, to your productivity software that you use to communicate with your customers, to the product itself. We're a software as a service company, so obviously our software generates a ton of data. And these sources, they're not uniform. You know, they're going to come in many formats: raw text logs, delimited formats, CSV and space delimited, JSON, could be some binary formats even. And those come in via different protocols. You know, some of you may not have to deal with syslog today, but a lot of people still do. Buckets are a common way of delivering logs as well. And you need a way to get that data into your platform easily. HTTP APIs via either pull or push are another common method. And then cloud event buses are kind of an up-and-comer in this space. So then once you've got that data into your system, you want to normalize it. Why do you normalize? Because you need to be able to do efficient queries on that data. But in order to do that, you're going to have to pick some kind of a schema. You're going to want to make sure that you have the essential pieces of data that you need. And you're going to need to track those things like timestamps and log sources. And then, of course, you're going to have to think about what goes into your normalization as well. So for example, if you do have those raw text logs, that may involve regexes, regular expressions, which there's some operational risks there, which we'll cover maybe a little in depth a little later. CSV logs also, if it's a perfectly standardized CSV, you're probably not going to run into any trouble, but sometimes you have quotes in the wrong places that then break your parsing. So normalization engines just need to be limited so that they don't run over, and they need to be able to handle erroneous data. Once you have that normalized data, you're going to want to enrich that. Enriching it provides the insights that you need to detect threats to your platforms. This enrichment data could come from internal sources like your enterprise data systems, you know, HR systems, things like that. Who's doing what? How do we attribute things? It could be metadata about your production resources. And it could also be indicators of compromise for your detective controls. So you may have specific indicators of compromise that are specific to your platform. This may also come from external sources. So those indicators of compromise could come from public databases. They're like things on GitHub that you can grab, or there are vendors that can also provide these kinds of threat data that you can use with your normalized logs. Finally, once you have the enriched normalized data, you can run detections on those to find the actual bad actors in your systems. This may be predefined indicators of compromise. It could be anomaly detection using statistical methods or unsupervised ML models, or maybe, everybody's favorite topic, large language models might be part of this in the future. But it's important to be able to run iterative development of those detections because they do change over time, and you want to be able to tune the performance as things change in your environment. And you also want to be able to reduce false positives because there's a human cost to this in the next step. Finally, those alerts go to the response team. They need the details about what happened and how they can investigate it. So you do need to have some kind of a system for alert delivery. Moving on to the last step, and then we'll get into the architecture. You want to be able to investigate what happened. So you're going to need the same data for that, right? One log source might indicate something's wrong, and then you need additional context from other sources. From that step, you can move to confirming whether it's a malicious actor or benign. Most of the time, it's going to be benign, but you still have to check every time that you get one of these events fire. In the case that it is malicious, again, just wrapping up kind of our Blue Team 101, you're going to want to contain that intrusion, close the vulnerabilities that may have allowed somebody to get in the first place, prepare and execute your recovery plan, and then, as always, whenever there's some kind of an incident, be it an operational incident or a security incident, you're going to want to conduct a lessons learned session afterwards. So this is what we want to do. Now, how did we actually do it? So we're going to jump in now to the architecture. So I'm going to go over kind of two parts of the architecture, the inputs and then the detection side, and then I'll show you just a slide briefly where we put the two together. So you can see on the left-hand side of the screen, we support multiple different source types. Those could be HTTP, API, syslog, buckets, etc. And those go into a series of lambdas. So we are an AWS shop, so this will be an AWS specific architecture, but this could be applicable to many other clouds. So those, we use lambdas for inputs, except in the case of syslog, which obviously it's not really easy to tie syslog to a lambda. So for that, you'd want to have a more traditional kind of compute platform with a load balancer. From those Lambda inputs, we then add the origin metadata and run it through Kinesis Firehose, which allows us to aggregate huge amounts of data into a semi-structured data bucket. And that's kind of our golden storage bucket where we do all of our work from. Once we get the data in, you can see that the same bucket is kind of down on the bottom left of this diagram. We can use both AWS's analytics tools and third-party analytics tools, which we connect to the same bucket. And this allows us to use the right tool for the job, which is one of the most important things that we try to accomplish with this architecture. So putting these two sides together, this is what the entire thing looks like. And it's a little, it's a little big, it's a little complex, but it's all managed by infrastructure as code, doesn't require very much, care and feeding at all. So now we'll get into kind of deep dives on the different parts of this architecture. So to begin with, we're going to start with the data collection, which is one on the left-hand side of that diagram that we were just looking at. So this takes the raw data and brings it into our platform. Now, as we covered previously in the overview, the data sources are extremely diverse. We have a preference for pull, and the reason you want to prefer pull for data collection is because there aren't as many reliability concerns with a pull data source. So a pull data source, caching is inherent. You grab the data when you're ready to receive it, and And generally, that's very, very straightforward and allows data buffer on the origin side. With a push data source, like syslog or an HTTP receiver, that increases the reliability requirements on that input. And the reason for that is that if your input goes down for, hours, days, then that data will be buffered on the source, maybe, and it will eventually be lost. It may be lost right away. So that's why we have a strong preference for pull inputs, even though we support both in our architecture. Now, the scale can be very large, so we needed an architecture that is, elastically scalable, cloud native, and we want that scaling to grow and to shrink as the input changes over time. So we want it to handle bursts, the old slash dot effect, right? And also just general seasonality of data where, nobody uses the platform on a weekend, so we don't really, need to be running a full capacity cluster at that time. Another goal is to have the cost growth be no more than linear with volume. So ideally, we can get some economies of scale as the volume goes up. The costs may not grow as quickly as the volume does, but at the very least, you don't want to be paying any more as you get more and more data because that limits your long-term scalability. We wanted a system that was required limited coding. So a lot of these inputs, we wanted collaborators to be able to help with this. Anybody should be able to get data to us. So we developed a system with significant wrapper functions that allowed you to write many types of inputs in just a few lines of Python. And we wanted to be resilient to failure and have health monitoring, which we'll cover the specifics of in a few slides. Most importantly, stay cloud native. Otherwise, you're going to be just paying extra and you're not going to be efficient on the cloud that you're running on. So for pull sources, the architecture for pull sources is kind of similar for all pull sources. One way or another in our architecture, a notification of data will arrive on an event bridge bus, and that will route to an SQS queue, which is in front of an input Lambda. The reason we use SQS queues instead of going directly from event bridge to Lambda is because SQS queues allow your Lambdas to run synchronously and give you some retry benefits. It's more able to redrive data if things don't go so well in your Lambda, which can sometimes happen. So after it arrives in that SQS queue, the function is triggered and the data is collected and written to that central Kinesis fire hose, which then goes into our bucket. Now, what about when it's an API that we're pulling from and it's not an S3 bucket? S3 buckets are pretty much the trivial case, but when it's an API, you may not get a webhook notification. I haven't really even seen that. EventBridge has a scheduler built in, which is an AWS service, but that scheduler does have some limitations. It doesn't have any ability to catch up if it gets behind. It'll just keep monotonically generating cron type events. It doesn't have sub-minute granularity if you need that. So we do have a tiny event generator for our pull sources, and that runs in Fargate, and it just generates events into our EventBridge bus that triggers those inputs. So this is kind of the visual of what that looks like. So as you can see on the left-hand side, we have log buckets, which generate bucket notifications into the EventBridge bus. And we have our job generator, which stores bookmarks in DynamoDB, but otherwise also generates into the same EventBridge bus. Those trigger those SQS queues, which trigger the Lambdas in turn, which pull data from either those buckets or public log APIs. And the logs, of course, are written to the Kinesis fire hose and then onto our bucket. Now, what about those push sources? As I said, there's syslog still exists in the world. You might need an HTTP receiver. AWS is pretty much completely optimized for building high volume HTTPS services. So similarly, we want to use a similar type of architecture. Lambda is a very good tool for this because it doesn't need to process things for long typically. So you can very simply meet this need by building a receiver Lambda behind an API gateway. Now, you'll need to make your own decisions if you're going to build something like this about how resilient you want it to be. Do you want to be in, just multiple availability zones within one region? Do you want to be in multiple regions and resilient across that? But in general, again, you can reuse the code from the pull inputs and use the same formatting and filtering that you would use in your push inputs. Designed for high volume, of course, so you do want to allow for batched uploads. If you do an HTTP request for every single log message, you'll quickly overwhelm even AWS's scalability. And finally, since this is a security talk, you do need to threat model an HTTPS input and decide what the risks are that you're willing to accept. In some cases, I don't think that it's particularly risky to have this on the internet as long as it's, write only being the important thing. But, your mileage may vary. Be sure to, threat model this for your own organization. Now, once you have that reliable log endpoint, you can then use collectors to collect things that don't speak HTTP. So, there are many tools for this. They're open source tools. They're easy to get, easy to install. And from there, you can make a centralized syslog collector and have that forwarded to HTTP, or you can pick up files from machines, or you can collect metrics, and that all goes into the same pipeline as everything else. So once again, we're all centralized. Everything, is hunky-dory so far. So what if something goes wrong, right? So obviously these things you do sometimes get malformed logs. You do sometimes get, a format changing. How do you detect that? So again, once again, we're using an AWS native architecture. So we use CloudWatch alerts to detect messages in dead letter queues from our SQS queues, too many messages, too few messages, Lambda failures, and the runtime of Lambdas, because there is a hard limit of Lambdas. You can set a limit on each Lambda, but the longest you can set is 15 minutes. So as you start to approach that, you do need to tune. Typically, we only see failures in response to somebody making a change. Again, you can see format changes downstream, but again, that's usually due to a human. Likewise, other failures with like runtime exceeded or things like that are usually due to some human as well. So we have not seen we've not needed a lot of care and feeding, and it's usually been traceable to something in our GitOps process. So now we've collected the data and we've put it all in a centralized S3 bucket, or actually as part of putting it into an S3 bucket, we are going to take this normalization step. We developed a companion system. Notice this is the normalization and enrichment step. We developed a companion system for managing enrichment data, which David will cover a little later on. But right now we'll just talk briefly about normalization. So we talked about normalization earlier, just the why. Again, structured logs are more performant and easier to analyze. And you also have an opportunity when you normalize to standardize your field names. So there are some common things like a username, an IP address that can make your analysis code much easier to write if you use a standardized format. We also have some instrumentation inside our normalization engine, which allows us to verify if something starts performing poorly, if we get less data than we expect. It's just another point of instrumentation in addition to our CloudWatch. One important choice when you do build your own normalization is whether you want to keep the raw message or not. So the whole point of normalization is to reorganize the message into something that's easy to use. Do you keep the original? For us, the costs are low enough that we have chosen to keep the raw message. That allows us to reprocess in the future if our schema does change. Now, I mentioned log schemas. if you're building from scratch like we did, you have an important, very important choice to make in what schema you use. There are some very high capability schemas that have a whole lot of, data types in them. They require a more advanced normalizer. And a more advanced normalizer requires more care and feeding. The more regular expressions you use, the more likely that something could go wrong. But some popular choices as far as those more advanced schemas would be the Elastic Commons schema or the Open Cybersecurity Schema Framework. Both of those have support by, fairly large chunks of the industry. But what did we do? So we decided to go with a very lightweight wrapper schema. As I said, that we are retaining the original message, so we have a fairly good ability to take actions further downstream on that original message or slightly restructured message. So we just have a simple wrapper that includes where it came from, what the metadata about how it got there was, when we saw it first, a deduplication ID, and the message itself, and a few other less important fields. Now, again, since this is an architecture deep dive, we're just going to briefly talk about how we actually accomplish that normalization, and that's what I consider like to be a cooperative design. The inputs give the basic format. They verify that the format matches what's expected, and structure it so that it's already in a structured data format. So it can be embedded into JSON without needing to then pull out the data later on. From there, it goes to Firehose, and Firehose has the ability to run arbitrary functions on the messages that go by in Firehose. So there's an additional normalization lambda there, where we can do centralized processing. For example, we can add enrichment data into the message if there's something that's going to be transient that we might need in the future. And we can also do some metrics on the data as it goes by in the normalizer. So that should wrap up the normalization phase, and we'll then move on into the detection phase, which David's going to take over for.
Oh, thanks, Brian. So going back to our original architecture diagram, thank you, Brian, for covering the left half, which is the very complex phase of getting a lot of different heterogeneous data sources and placing them into a single bucket where you have a nice source of truth. And right now we're going to focus on the right side of the equation, which is what do we do with this data from a detection response function when it's actually flowing into our kind of data lake. So taking kind of one quick step back, what is a detection? Blue Team 101. Really, we're looking at some sort of data source and trying to identify whether malicious events are happening that somebody needs to either respond to either automatically or manually. And for us, we kind of have broken it up into two different classifications. We have streaming style detections where you're looking at events as they come in one by one. A good example of this is, you're looking at network traffic. You have a host which has reached out to some IP or some domain that is associated with a malicious actor. That event in and of itself, that JSON payload, is enough to tell you that, hey, something is wrong. You can look at those events kind of one by one. They have self-encapsulated context. A bit more complicated is the batch detection, where you're actually looking for additional context and additional information of the same kind of events over time. A really good example is the MFA fatigue attacks that have been happening pretty frequently and were in security news a couple months ago. But essentially, if you think about detecting for an attack like that, where you're having a user who's consistently getting MFA auth requests, if somebody fails an MFA auth request one time, that could be normal, right? You hit the wrong button on your phone, your Face ID doesn't work, something happens. But if you see activity where you're having a user consistently failing it 3, 4, 5 times in a span of a few minutes, that might indicate a little bit more that something bad is actually happening. So we have kind of these two different categorizations for detections that we look at. Really want to talk about how we manage detections as well. There was actually a panel right before this, which seemed great. Highly recommend checking that out. That kind of covered this topic in more detail. We just wanted to touch it really quickly. So taking components from software engineering principles, Brian and I are software engineers by nature. We're builders at heart, spent a lot of time kind of in those kinds of workflows. And for us, it was really, really important to kind of take those principles and align them to our detections as well. So if you think about detections not as a detection, but as some sort of software service, and you shift your mental model a little bit, there's a lot of parallels that will happen. So you want to be able to write repeatable detections. You want to have a centralized source of truth for them. You want to be able to test them, upgrade them, roll them back in case of a bug. And you also want to be able to promote them across different dev and prod environments. So by the time a detection or your software service gets to a production environment, you should have full confidence in its ability to do the job that you want it to. Testing, both in unit tests and integration testing, is something that we really wanted to have as well to ensure a really high bar for our, again, software services, in this case, detections. So wanted to walk you through kind of the detection workflow that we've kind of come up with that we've built out, has been working pretty well for us. So I'm kind of skipping the initial phases of the detection lifecycle where you would gather your requirements, you'd come up with a hypothesis. This is more when you've kind of have a little proof of concept and you want to start working on a tangible detection. So we start off in a dev environment. We purposefully have a delineation between our dev environment and our production environment. Again, just going back to that testing story, you can make changes, you can try new things out without risking any downstream systems. We have two similar data flows in both our dev environment and in our prod environment. To keep costs down, we do data sampling in our dev environment, but you still have a very real stream of data that's coming in, with certain contextual requirements, if the data is okay to be in dev. And then that gives you a really nice environment to test things out, prototype things, and again, without having the risk of impacting something in production. So you do your local development, you write some code. Next thing that happens is, as with the software service, you're going to write some sort of unit tests. Unit tests get committed to a GitHub repository. That kicks off a deployment. And once the deployment happens, we also have an additional step of continuous validation. So if you think of a web service or a website, it's pretty easy to know when issues are happening. The website won't load. Latency is super, super high. Maybe there's error rates that are happening on the back end. But for detection, you don't really necessarily know how often it's going to or not going to fire. In fact, for some of your very high fidelity detections, ideally, depending on the environment you're in, they shouldn't really ever fire at all. So we really wanted to have some sort of continuous validation system to ensure that the detections that were written, 1, 2, 3 years ago, maybe by someone who's not even on the team anymore, are still doing the exact job that they were designed to do from day one. So if all of these steps pass and the noise level is acceptable, continuous validation is good, we will simply do a promotion process and deploy it in our production environment where we still get the continuous validation consistently. So I've talked about this continuous validation step a couple of times, and I want to dive into it a little bit deeper. And one thing I also want to call out is that when Brian and I were building this system, we were kind of faced with a fair amount of work to do to go from scratch to something functional. And for the detection engine, we kind of needed to figure out if it was something we wanted to build or something we wanted to buy. For a variety of different reasons based on engineering constraints and a couple of other factors, it was also really important for us to be able to immediately deliver value to the business. So as the business is investing in a detection and response function, we needed to be able to kind of show value pretty quickly. And so we chose to kind of buy a detection engine so that we can build workflows on top of that, gave us a nice foundation to get started, and let us invest in some really, really neat efforts to guarantee a high level of service, for instance, continuous validation. So on the detection health system, I think I got a little bit ahead of myself here, but essentially your detections can only help protect the business if they're actually functioning and if they're actually working. Unit tests are great. When people talk about detections as code, there's a lot of talk about unit tests, which is fantastic, but they're not necessarily enough. To go from a raw log to a response action, all the steps in between, there's a ton of different interconnected components. You can have bugs, you can have bad deployments, something can be failing along the lines that, you might not have monitoring for, you might not have thought to build monitoring for. So we really needed some sort of fully functional end-to-end integration test. One other thing for us is we wanted to keep in mind that writing detections is hard. Writing complex detections is hard. You go from the requirements phase, you go through your prototype, you build it, you test the noise level, you tune it. The last thing we wanted to do was come up with some sort of process which would, upset detection response engineers and want them to bypass the testing process. So we wanted to build something which was low friction, easy, and would make our DNR engineers want to write tests because it would give them a benefit versus something that, they would just have to do because we put a checkbox and then they'd kind of stop doing it after some time. So our detection health system has two different components. The first is generating Canary alerts. So what we do is we built a system that takes synthetic data, fires it into our detection pipeline, and then that flows downstream. There's a couple of different components here. You'll notice very similarly, we have actually event bridge rule, which kicks off a Lambda on a cron job. Lambda has monitoring with CloudWatch alarms, all the built-in native integrations. Again, taking a cloud native approach has been extremely helpful for us. We put Canary data in an S3 bucket that the Lambda will read from, and then it will fire it into our detection pipeline, which Kinesis Firehose, it will take the data, it will send it into our centralized source of truth S3 bucket. What we do with the Canary data is we mark it in some way to determine that it is actually a Canary event. If so, in our downstream automation, downstream processing, typically this will be a SOAR platform, we short circuit, so we make a note of that event, but we don't generate anything that a human would need to interact with. We don't cause additional alert for an analyst or a DNR engineer. There's no extra work that's generated from this. So it only really raises noise if Canary events stop firing. If it's not a Canary event, if it's a real thing, of course, we don't want to get in the way of any alerting there. So it just proceeds with the regular flow. One other thing I want to call out is the reason why we chose to start with synthetic data rather than building a bunch of different environments to kind of write scripts to generate real data is due to the heterogeneous environment that we operate in. Brian alluded to it with all of the different data sources, SaaS companies, so lots of different environments and integrations. Rather than spending the time to kind of build out and mimic every single environment and every single offering that we wanted to keep track of, we felt that we would be able to provide value more immediately and faster in achieving our goal of kind of maintaining a high bar of detections by choosing to use Canary events. Down the road, the intention is to kind of take the most common environments and swap out the Canary events for real events. That's some future work that will be done at some point. The second component is actually sounding the alarm or being the Canary in case a detection stops firing. So every single time a detection fires, it gets written to a detection table, which is actually also used for our batch detections. So there's a record of all of that. A Lambda will query this table with a CloudWatch rule consistently on a cron. It will take these metrics and report them as CloudWatch metrics. CloudWatch metrics will have alarms tied to them. So if for some period of time, hours, days, whatever your threshold is, there will be an alert that fires if there's no Canary event that has run through. So what we did was we took kind of all these two components and we abstracted it away in a Terraform module, very similar to how Brian talked about having a Terraform module to allow for easy repeatability for onboarding new data. We really wanted to maintain kind of a similar approach for these for the detection health system. Again, just being mindful of the fact that we don't want to get in anyone's way. We want to empower people to take advantage of this kind of free testing. So all it takes is instantiating a Terraform module. It's like 4 lines of code and uploading a file to S3. So very, very low friction. You get free monitoring for your detection, knowing something's wrong. The next section is called alerting, but it's actually a trick. It's not necessarily alerting yet. So just because you have a detection that's fired doesn't necessarily mean that you're ready to generate an alert. And the reason for that is how much context does your detection have that's already fired? Context is key because if you just have detections alerting humans or sending stuff into a queue, very quickly you're going to hit alert fatigue, you're going to have a huge backlog, and it's not even going to be helpful. You're just going to have too much stuff that's firing. A lot of it is probably not even important or is benign, so you need context to be able to filter things out and suppress them accordingly. I want to walk you through a basic enrichment example of how a detection can fire, but by enriching it and getting additional information, you can triage it a lot faster and have much better understanding when someone begins an investigation. On the screen is a sample guard duty alert. So this is not a real alert. If you use the service, you can click a button and it will generate some fake alerts. You can see the EC2 instance ID is not real. But in this case, it's simulating a real guard duty detection firing. Also, guard duty is Amazon's native threat detection service. So you can see that there's an EC2 communicating outbound with a known C2 server. I blocked out the account, but there's an account number in there, and you kind of have a description of what's going on there. So when this alert fires, if you see it and you send it to someone to take a look at, you know something is wrong, right? You have some sort of host, it's communicating with things it shouldn't be communicating with, what's going on. But the immediate questions you're going to ask are, what is this EC2 doing? Whose EC2 is it? Is it important? Is it a build server? Is it like a one-off kind of research thing? Is it a production server where taking down the server will impact a production workload and you have to take a completely different set of response steps? There's a lot of context that kind of gets built in. Who owns this EC2? Who's the service team? What kind of stakeholder are you going to be working with? You have very similar questions around the account portion. Who owns this account? Again, who are you going to talk to? How important is this account? Is this a legacy account that's been forgotten about? Is there extremely sensitive data in here to the business or from compliance perspectives where all of a sudden you know this is P0, all hands on deck? Lastly, this one is a little bit more of a stretch goal, I guess, but if you have threat intel feeds that you subscribe to, or maybe more mature threat intel capabilities, you can maybe track the IP or the domain and say, hey, is this associated with the threat actor that we're tracking? Have we already been hit by this threat actor during a different campaign? What do we already know about this? So that can be helpful as well. Brian touched on it earlier, but the way that we do this is with our enrichment architecture. So again, to add context into detections when they fire prior to an alert just being created, there's a couple of different steps here. But the main building blocks are the same ones that we've been demonstrating throughout this entire application. So we have an enrichment data source. Again, it can be external, it can be internal. You got data that can be useful somewhere, and we query it with a Lambda on a cron job, which in AWS is an event bridge scheduler. So the Lambda will take this data, it will write it to an enrichment table, which in our case is DynamoDB. The reason why we chose it is because it's great for unstructured data. It's easy to use, scales, has really easy integrations with things like SOAR platforms, et cetera. Just gives you a nice little hook to query the data. Brian actually wrote some really neat code to do some deduplication between data that comes into that enrichment table. So making sure we're not just consistently writing the same data over and over again. We're only doing updates when there's a change in whatever enrichment data that we're recording, and some neat sequencing for different point in time interactions as well. The rest of the steps are kind of to convert the data. So in our streaming alert and SQL search tool, to integrate this kind of enrichment capabilities, it expects the data in a CSV format. So we have some functionality to take it from this kind of source of truth DynamoDB table, convert it into a CSV, and feed it into our streaming alert and SQL search tool so that we can take advantage of this data as well. So now we're at the investigation phase. So we had a detection that fired. We enriched it with some context. We decided to generate an alert. We're not going to suppress it. And then now we're at the investigation phase. So continuing with our guard duty example, we still have some questions for how we're going to do this investigation. So we got some more context, but we still have a list of questions that we need to answer. And this is more of, hey, if you have an investigation that's going to happen, most of the time, depending on the maturity of your program, what your environments look like, there could be a lot of maybe basic things that can be a lot harder than you think. For instance, do you have access to this AWS account to come in and take a look at this EC2 host that fired an alert? Can you even get access to the EC2? Do you have SSH keys? Do you have SSM? Do you have some other way of interacting with the box? Do you even have an IAM role that you can use to take a snapshot of the EBS instance? If you want to do forensics on the machine, in AWS, it's not as straightforward. There's a couple of different steps along the way. And when you kind of want to take a snapshot of it, you want to also boot it in some sort of isolated environment. So if there's malware running on a host, you don't just want to take it and start running it in VPCs inside of your network. You probably want to create some sort of isolated environment. Maybe you have some pre-installed tooling on a workstation and you can do forensics on, PCAPs and all that. So the way that we kind of think about this is if we fail to prepare for these kinds of investigations, we're not really going to be supporting our DNR engineers or our responders when investigations come in. So at the investigation phase, again, when a human starts to look an alert, this is typically where you're going to have a lot of bottlenecks because it requires manual effort. Again, you're going to have some automation in place, but eventually you're going to have alerts that are going to come in that physically require a human to come in and take a look at. So what you want the responder to be able to do is to answer the questions and finish the investigation instead of getting bogged down in things like, how do I get to this EC2? How do I get to this account? So the way that we do it is we try to have a mentality of ruthlessly automating everything that we possibly can. If it takes more than a couple minutes, or if it's something that's painful or hard, we build out some processes to save time and, more importantly, minimize mistakes. So we really make this kind of conscious investment in setting our responders up for success. One way that we do this is by building a forensic workstation. So what we do is we leverage Amazon's EC2 image builder service, and we kind of create this workstation that any analyst or any person on the security team has access to in a security forensics account. So we create this EC2, we boot it, we create an AMI, we load up all the software that's necessary to do these kinds of forensic workflows. Then we publish it, we tag it, make it available to whatever work streams need it. Or if someone just wants to boot it, attach an EBS volume, and then go to work. This diagram turned out much better on a big screen than I thought, so pretty stoked about that. So the other thing that we do is we actually decided to automate forensic extraction. So going back to this guard duty example where we have an EC2 that fired, we want to do some sort of research on it, answer some questions. There's a lot of steps in AWS. If you have an arbitrary account and this alert fires for an arbitrary region, you need to have a role that can take snapshots of these EBS volumes. You need to copy them to the right region. You need to encrypt them. You need to have the appropriate KMS access keys so that your security forensics account can decrypt the EBS snapshot and then mount it onto an EC2. Again, you want that forensics environment so that you can comfortably boot up the EC2. And there's just a lot of things involved that can take, honestly, a couple hours if you're going through it for the first time and you're not super familiar with the environment. So we wrote some tooling around this. We wrote some scripts to take a process down from a couple of hours to a couple of minutes, where the bottleneck is not access to your AWS resources, knowledge of AWS, or anything else. The bottleneck is just how long does it take AWS API calls to execute. You get a forensic workstation booted up with these volumes attached. You can begin your investigation without having to worry about anything else. If you've made it this far, to the response portion, congrats through the day, through this talk, and also through your detection and response function. So now actually is where the real work begins, right? So you have to fix whatever is wrong. You have to assess whatever issues have come up. You have to deal with the ramifications of it. You have to do the fire drill of getting the right stakeholders in place, following your runbooks, et cetera, et cetera. But there's one other really important component of the response piece that I want to call out, which is remembering to evaluate your detections. This is detection lifecycle. This image is not mine. I took it from the Snowflake blog. They have a really great article about this, which I really, really liked. And so there's a component here which is called monitoring your detections. So we've already talked about the continuous validation phase where we have some sort of integrated testing to monitor our detections, make sure they're working. And this isn't monitoring in the sense of, hey, I want to see how performant my code is running, what the latency is. This monitoring is from the context of how effective is this detection? How noisy is it? Are there additional signals that we could have inserted into the original detection that could have saved a responder time later in the investigation? So even after the response phase kind of finishes, Brian alluded to it earlier at the start of the talk in the overview, but you really want to make sure that you kind of go back and maintain these detections as you would maintain a software service over time as it's running. So Brian and I spent a lot of time on this, and we're pretty proud of what we built. But we also had some learning, some things that went well, some things that didn't go well that we kind of wanted to share. Some things that have been really successful for us are automating onboarding of new data sources. So just making things as fast as possible. So folks who aren't necessarily as comfortable with Terraform, maybe as comfortable with Python, just don't have time to do it. We don't want to be blockers for them to onboard new data into the pipeline for their own use cases. Scale has been great. Again, taking a cloud native approach lets us scale really well, very cost effectively, notably with the Lambda and the SQS. Following the detections as code paradigm and taking software engineering and applying it to our DNR function has resulted in pretty well tested and high quality detections where we have very high confidence by the time a detection ends up in production that it's going to run. Something is continuously checking, looking after it. And yeah, overall just building a lot of confidence. And enrichment system is something that's been great for us, just adding that context, helping us get through investigations faster and able to prioritize things that come into the queue. Some things that we definitely want to improve on over time is empowering folks. Again, I outlined this as a positive, but it's also still a work of improvement or area of improvement that we can work on, is onboarding new data can still be sometimes, depending on the data source, a high touch process. So we want to make this as self-service as possible. So there's some continuous improvements we can do to make onboarding data even easier. Want to continuously improve our CI/CD story, and this is mostly for me, but have hit some parsing struggles. I wrote regex, which wasn't great some time back, and so just making sure that when we do those things and we wrangle log sources that are a little bit messier, we take the time to kind of do it and flesh it out as much as we can before deploying it anywhere. Since we've built this system and have the opportunity to kind of present this, there's been a couple of other alternative approaches that have come out, or some other systems that have come out. We haven't used any of them. They all seem really cool. This is not a vote of confidence for any of them, just something that we would look at if we were to rebuild the system from scratch again. AWS has an offering. It's called AWS Security Lake. Its goal is to centralize a bunch of data. Marketing is really, really good. What they do is they leverage OCSF, one of these security schemas that Brian called out at the start of the talk, Open Cybersecurity Schema Framework, to help out with the log normalization log normalization aspect of it. So you have this nice kind of centralized data lake, if you want to use that term, where you have a schema in place. Matano, not sure if I'm pronouncing that right. This is open source version of it, and also a detection engine on top of that. So it's really, really neat. If you look at the GitHub, they have architecture diagrams which look similar to what we've built. So that was really nice validation for us in terms of the approach that we kind of pursued. And they leverage the Elastic schema, Elastic Common Schema, for their log normalization. And they do something really cool. They leverage a vector remap language to normalize logs. So kind of taking that compute portion and the normalization. It's a really neat way to do it. So I'd highly recommend checking that out if you're early on in your journey. Lastly, this is more on the detection validation side, but Datadog released a tool called Threat Test. It also integrates really nicely with their attack simulation platform, where we can fire up detection that's mapped to MITRE. You can execute it, and then you can use this threat test framework to make sure that alerts fired on this specific workflow that you kicked off. Seems really, really neat. So to tie it all together, we started off with a need to go from a raw log to making a security decision. And it sounds pretty simple, and it is at lower scales, but as you get more data sources, more scale, it can start to get a little bit more complicated. So we walked you through kind of the 6 different phases. You have the raw data, normalization, detections, alerts, investigations, response. And there's a lot of different work streams that you can take along the way to kind of make this process as high quality and as useful as possible for the detection response side and for the business as well. So we definitely didn't cover everything, but hopefully this can be a helpful blueprint for building out a scalable and cost-effective threat detection platform with a high bar for quality and reliability. And with that, I'd like to thank you all for your time, for coming here, and would like to open up the floor to any questions. Question? Yeah.
What detection engine did you guys?
The question was, what detection engine did we use? We purposefully left that out because we didn't want to endorse or turn this into a vendor talk. I would be happy to answer that literally right after this. Yeah. Next question? Yeah.
So right now we are kind of peaking in the tens of thousands of events per second, which is not that big, but we do have every expectation that this could grow to, millions of events per second if we need it to.
Question. Question was, any plans to open source any part of it? I have to ask the boss, I think, on that one. At this time, not that I know of.
So there's not any open source yet, but there is. I did publish a blog post on the benchling.engineering site, which is our blog, which does cover a very tiny piece of what we used, which is a JWKS exporter for KMS asymmetric keys. So again, just as kind of like a breadcrumb of, we're not entirely opposed to it, but we're just kind of dipping our toe.
Don't see any other questions, but Brian and I will stick around right after. So thank you very much again for coming to our talk. I hope everyone has a great weekend, great conference. Thank you.
Thanks, everyone.